The first stop that we are going to see is Hearst Memorial Mining Building. The building was first built in 1907 and was renovated in 1998 with a great earthquake-resistant system. At the back door of this building, we saw a great gap on the ground. After the explanation of GSI, we noticed that this empty space can help reduce the effect of the lateral move during the earthquake. After we reached the bottom of the basement of the building, we suddenly saw a giant base isolator. From our GSI, we know that this building has 134 base isolator that support it. The isolators can move 28 inches in any direction. We suddenly noticed an interesting part of this building. This building used mostly flexible tubes that can still be stable during the earthquake to prevent the dangerous consequence after the earthquake. And we also saw some curves moving and the curb reconstruction on the outside of the building. The second stop is near Berkeley Memorial Stadium. It is on the halfway of the hill. The name of this big cement cube is borehole transmitter. A lot of transmitters around this area help us collect real-time seismicity information from this area and transmit the signal to Berkeley Seismicity Lab. Meanwhile, after we saw the transmitter, on our way to the stadium, we saw a little crack on the ground. This crack notifies the existence of the Hayward fault. The next stop is Berkeley Memorial Stadium. The stadium was built in 1923 as a tribute to UC Berkeley alumni who fell in World War I. It involved bringing 250,000 cubic years to build it. It historically destroyed the Hayward fault, a short ridge that blocked the stream and deflected the flow of Strawberry Creek to the north. However, this creates a danger of earthquake liquefaction during the earthquake. The GSI also showed us a map to prove it. This map shows the shorter ridge on which the stadium was built. Now the active trace of the fault goes through the stadium and past the corners of both halls. Because the constructors have already considered the danger of the earthquake when they built the stadium, they actually built two parts of the stadium instead of making it as a whole. There are two houses of the stadium and joined by the vertical expansion joint. So there is a gap between one half of the stadium and another half of the stadium in order for them to move during the earthquake. There are also lots of damages to Memorial Stadium during the Hayward fault. A. At the south end of the stadium, the expansion joint at section KK has opened more than 20 cm at the top. Underneath the stadium in this section, you can also see tidal support columns and cracks in a wall recently built into the stadium. Meanwhile, the gap is way bigger at the top than the bottom because the ground helped release a little bit of energy during the earthquake. There are three types of cracks present in the stadium walls: horizontal cracks, vertical cracks, and diagonal cracks. Typically, the horizontal cracks are due to the construction-related problems, while the vertical cracks are the result of differential setting. The diagonal cracks are usually caused by the fault-related movement. They also use a lot of flexible tube and flexible conjunctions during the construction in order to prevent the dangerous result of the earthquake and make the stadium much safer. The next stop is Hamilton Creek. Even though there's no water in the creek now, but we can still observe that the creek turns really sharp in 2 points. Meanwhile, we also notice that the portion between two sharp bends lies right on the Hayward fault. Hence, the Hamilton Creek provides enough evidence for the existence of the fault and make us know how a fault can do to a creek. The next stop is the last stop of our trip, which is Dwight Way. We can clearly notice the distinct displacement of the curb to the right. It showed the existence of the Hayward fault as well.